in this example, this result was correct. Okay. Some of you told me. Some of you told me that there should be 12 types and 3 elements, but it is the other way around. Okay, so here the types, we have exactly 3 compartments. Okay, first compartment corresponds to the value of x1. The second compartment corresponds to the value of x2, and the third compartment corresponds to the value of x3. Okay, so let's say that you give 6 tokens here. 1, 2, 3, 4, 5, 6. 2 here and 3 here. Then you have a solution to this equation correspond to x1 equal to 6, x2 equal to 2, and x3 equal to 3. Okay. So effectively, the number of separators here is 2, which is the number of variable minus 1. So here, this one here is R combination, so this should be maybe 3 again. Okay, so here this one is N. Okay, this one is R. And so here, when we talk about R combinations of N elements, that means that N is the number of types. Okay, N types, and we allow repetition in order to obtain a set or a collection of R objects in N types. Okay, so the answer to this example was effectively 78, but not 91 as we said last time. Okay. Let me maybe show the participants.
Recording in progress.
Okay. So onto the next type of commutations with repetitions, we would like to look at this example. Okay, so here we have a certain number of objects. Here in this example, the question is to find the number of strings that can be obtained by shuffling the letters of this word, success. Okay, so now you can see here we also have three types, 4 types of objects, okay? And they are allowed to be repeated. But here the difference in comparison to the previous case is that here the number of repetition is fixed, okay? So here you have to find the strings in which there may be there are the letters S, U, C, and E, but if in the previous example, in the previous section, you can use an arbitrary number of each letter. Then here, now we want that there are exactly 3 S's, 2 C's, 1 U, and 1 E. Okay. For example, 3 C S S E S U S is a permutation of this word. Okay. R U E S C S C S is another permutation. Okay. So the question is that if we fix the number of times each letter is repeated, then what is the total number of such permutation can we obtain? Okay, so here, in fact, in this type of counting the number of permutation with repetition, it is you can see that some of you may have already found the answer. It is quite more simple. It's simpler than the previous case. In fact, here you know that there are exactly 7 places. Okay, you have 1, 2, 3, 4, 5, 6, 7 places, and then you have to find 3 places for the letters S. Okay, so in order to choose 3 places out of 7, you have 7 choose 3. Okay, and then once you have fixed the letters S, there are 4 places left, and you will have to determine 2 places for the letter C. So 4 choose 2, and then you have 3 places left. For example, here you can put S here, S here, S here. Okay, there are 1, 2, 3, 4 places left. And then if you put C here and C here, and then there are 2 places left. And in order to choose one of the 2 places for the letter E, you have this. And finally, there is only one choice left for the letter U. Okay, so this is the formula to count the number of permutations of this word success. Okay, so it is easy to understand. It's much easier than the example of cookies, right? Okay. Okay, and in fact, what I have just described to you was the second approach. Okay, and then in the second approach, we have used the product rule. We have a procedure of 4 steps. Okay, the step 1 is to place the letter letters S. Okay, 3S. Step 2, you place the 2 C's. Step 3, you choose a place for 1 E. And of course, you can change the order of the steps. Okay, they are interchangeable. So nothing forbids you to choose a place for the letter U first, and then choose the place for the other letters. And you can verify by a simple calculation that the order of places that you do is not that doesn't matter here. Okay, so that was the second approach. And what about the first approach? The first approach, you will use the division rule. Okay, so you know that if you shuffle all the letters here, you obtain 7 factorial. which is the number of permutations of the 7 letters. Okay. But here, since there are some configurations which are repetitions of another. For example, you can put the first S here, the second S here, and the third S here. That makes you, if you only count the number of permutations of all the letters, then it will. So then these two configurations will be the same. Okay. This configuration was counted for this one and for this one, and in general, since you have 3 S's, each of such configuration is repeated 3 factorial. Okay, which is the number of ways to shuffle the letters S among themselves. Okay, and similarly, since there are 2 letters C, you have 2 factorial repetition for the letter C, 1 factorial for the letter E, and 1 factorial for the letter S. Letter U. Okay, and you can verify that this is the same. You can write the formula for the binomial coefficient to see that it is the same as this one. Okay, it's exactly the same as shown here. So in general, if you have n objects in which there are some among them are the same as each other. Okay, so in general, suppose that you have n objects, and among which there are n1 objects of type 1 which are the same, and 2 objects of type 2, and so on until nk objects of type k. Then the number of permutations of these objects with n1, n2, etc. until nk repetition is given by this formula. Okay, so this formula is easy to prove. You can use one of the 2 ways given in the previous example. Okay, you can either use the product rule. You choose the places for the each type of objects sequentially. Okay, or you can take the total number of permutations and divide it by the number of repetitions. Okay, is it clear? Okay. So where is the wait a little bit. I have to take a screenshot. Where is the Okay, so onto the next part of this lecture. Okay. So here we look at this is called the 4-way counting. Okay. So here let us consider a general setup in which we have a number of balls and we have a number of boxes. Okay, so the question is, how many ways are there to arrange the balls into the boxes? Okay, and of course, in order to answer the question, we have to make precise. We have to know precisely which setting we are working on. Okay, for example, are the balls the same, or are the balls different from each other? And similarly, are the boxes the same, or are the boxes identical to each other? So here you can see on the slide, you can see on the slide that we distinguish 4 cases. Okay, so the first case is who is drawing on the board. Okay, so here we have 4 cases. Okay, so you have, if you draw a table here, and there you have the ball here, balls, and you have the boxes. Then we have 4 cases. Okay, the first case is the balls are the same, and the second case is the balls are different. So now you know the product rule. You can easily see, since there are 2 cases for the balls and 2 cases for the boxes, we will have, by the product rule, a total of 4 cases. Okay, so we will look at the 4 cases from the easier to the more to the more difficult. Okay, so we have the 4. So this one is here, identical ball. Sorry. So different ball, different cases, boxes here. Same ball, different boxes. Different balls, same boxes here and here. Okay, so we have 4 cases. So now this is the easier way to do. So this is an easier easy case. Okay, so suppose that we have n different balls and we have k boxes, and we want to put the balls into the boxes so that the number of balls in the box in each box is fixed. We know that there should be n1 balls in the first box and 2 balls in the second box, and so on. Okay, so this is exactly what we have seen in the previous section. So we have a formula here, and of course, if the number of balls in each box is not fixed, then what can we can we find the number of ways to arrange the balls into the boxes? Okay, but here, since the balls are different, it only makes sense if we fix the number of balls in each box. Okay, so here is an example in football. You know that in many major football tournaments, there are there are teams, okay? Normally there should be 24 or 32 teams, and they are divided into groups of 4. So if, of course, in reality, the number of way to divide the team into groups is much smaller, because there are constraints, there are conditions. For example, in European football, in the group stage, teams of the same country cannot be in the same group, and so on. So, but here in this theoretical setup, if we ignore all the constraints and we only count the number of ways to randomly distribute these 32 teams into 8 groups of 4, then according to this formula, you got this, and you can take out your calculator to see what is this value. Okay. So let me see if we can calculate it. Okay. So if we input it into Wolfram alpha, then this is the result. So you can see it is a gigantic number. Okay, how many digits are there? So it has roughly 25 digits. So it is an astronomical number. Okay, but of course in practice there are many constraints. So the real number is much smaller than this number. Okay, so that was the easy case. And now this case is also a setup that we have already seen. Okay, so here you have identical balls. That means that the balls are the same. We cannot distinguish them from each other. And different boxes. Okay, so what is this case? Have we seen the solution to this case? So this is exactly the case where we have the cookies. Okay, so this is the cookie case. Okay, okay, so here we don't have any conditions or the number of balls in each box, and you can see that this is a case that we have already seen, so we will skip it. And a new case is a little more complicated, which is different balls but the same boxes. Okay? So here, let us illustrate this with an example. So here, in this example, it is stated that you have 4 different people and three 3 offices. Okay, the offices are the same. And how many ways can you divide these people into the offices? Okay, so let's call the 4 people A, B, C, and D. Then the first way is that is for you to list all the possibilities. Okay, so these numbers are small, so let us try to list all the possibilities. Okay, so the first case is when the 4 employees are put into the same office and the 2 other offices are left empty. Okay, and note that since the offices are the same, this is consider the same as this case here. Okay, so if you put the 4 employees together in another office, then these 2 cases are considered the same. Okay, so that is the meaning of indistinguishable offices. So the second case is when you have ABC in one room and D in another room. And of course, you can also have ABD and C alone, or ACD and A alone, and B, sorry, it should be B, okay? B, C, D, and A. And finally, there are cases where they are divided in pairs. Okay, you have AB, CD, you have AC, BD, then you have AD, BC. So are there any other cases? And of course, there are A, B, C, D, A, C, D, D, A, B, C, D, and what else? We can have B, C, A, D, or B, D, A, C, and C, D, A, D. Okay, so in total, how many cases are there? We have 1, 2, 3, 4, 5, plus 3, that makes 8, and 14. Okay, so here, since the numbers are small, you can enumerate, you can list all the possibilities, but you have to be a little careful, because here, if you also consider the case CD, AB, then in fact you have counted this case twice. Okay, so this is not a separate possibility because it is already here. Okay, so here you can think of so here your intuition maybe to distinguish the cases where first we determine the number of people in each office. So you have 400. Okay, correspond to this case. In the 3 cases here, respond to the configuration 310. Here you have 2, 2, 0, and here you have 2, 1, 1. Okay, but the difficulty here is that if we consider this configuration and we try to choose 2 people to put in the first of this here, and then 2 people to put in this here, then we have counted this case twice. Okay, we first choose AB here and put CD here. But if the first time we choose CD here and then AB here, then we have actually counted a case that was already there. Okay. So it is a little complicated, but it can be proven mathematically. So if you are interested, we can. Okay. So in order to a good way to solve this problem is to before, as I said, before you list all the cases, you try to divide them into smaller categories according to the numbers of people in each office. For example, here, then you count each separate case, and here there is an interesting question: why is it not 6? Okay, and here why is it not 12? Because if you use the formula, if you use the formula for the case of distinguishable ball and distinguishable boxes, then you know that for this case, you should have something like 4 choose 2 times 2 choose 2, which is equal to 6. Okay, and here you should have something like 4 choose 2 times 2 choose 1 times 1 choose 1, which is 12. Okay, but in fact, we don't have 6 or 12 cases, but only 3 and 6 cases. Why? So that question is for you to think about. Okay. So here, in general, this is in fact, it would be easier to understand if you are able to prove this formula. Okay. But here, since not all of you are strong in mathematics deduction, I will just give you this formula here, and do not worry, because in the exam or in the test, you are allowed access to documents. Okay, so you don't have to memorize these formulas by heart. Okay? So basically, what you need to take away is that this kind of number is called the Stirling numbers of the second kind. Okay? So if you have done a little calculus, you know that there is a famous Stirling formula for the approximation of n factorial by the exponential function. Okay, so this is the same mathematician Stirling. Of course, if you look at the exercises in the book of Rosen, there will be mention of the Stirling numbers of the first kind. Okay, but here we introduce only the Stirling numbers of the second kind because it is related to our problem. Okay, so this result say that if you have n different balls and you want to put them into k identical boxes, but remember, we impose this condition so that every box is not empty. It means that every box has at least one ball. So under this setting, the number of ways to put the balls into the boxes is the Stirling numbers of the second kind, denoted by S for Stirling, and you have the two parameters here, n and k. and it is given by this formula. Okay, so for those who are interested, you can look at the I don't remember. I'm not sure if there is a guide for the proof of this formula for Stirling numbers of the second kind, but it is feasible. You can ask your teachers in tutor class. Okay? It amounts to count the number of onto function. Okay? It is related to the number of onto or surjective function in Vietnamese, toàn ảnh. Okay? So in English, it is the surjection. Okay? So you can okay, so it is the proof, but if you are interested in the proof, we may talk about it later if we have time. So in general, if we omit the condition that every box must have at least one ball, then that means that the number of non-empty boxes can be any number between 1 and k. The above example. Okay, so here we have 4. So in the above example, we have to calculate as 4, 3. Okay. So according to this formula, we will take, so k is equal to 3. So we have 1/6. Inside we have, if I is equal to 0, we have the sign plus. We choose 0. 3 to the 4. Okay. And minus 3, choose 1. 2 to the power 4 plus 3, choose 2. 1 to the power 4 minus that's all. That's it. We only have this amount of. So is it? So will this give us 14? So this was 1 times 81 minus 3 times 16 plus 3. But in the previous case, we allow the offices to be empty, so it will be a little bit different. Okay? So here we have 1/6 of this, and can someone quickly give me? So it is should be 6. Okay. This is 48. This is 81. Okay, 6. So this corresponds to the cases where all the offices are non-empty. So that corresponds to, if all the offices are non-empty, then we have this configuration 211. Okay. So if you remember, we had exactly 6 cases here. So we have A, B, C, D, and so on. Okay. So if you would, so this is equal to 6. So now we will calculate the other 2. So we also have the cases where there is only one non-empty office. Okay. So the solution to the previous example is equal to S So the second number here corresponds to the number of non-empty offices. So we have to calculate this sum. Okay? We always have 4 employees, but the number of non-empty offices can be 1, 2, or 0. And so this we already know that it is 6. And this, if we apply the formula, then we have what do we have? If k is equal to 2, we will have 1/2 of. So the first one is always plus 2 choose 0 and 2 to the power 4 minus 2 choose 1 times 1 to the power 4. That gives us so how many ways are there? So this should be 16 minus 2. That gives us 14 divided by 2, which is 7. Okay. And here the last one, we have only one term. Okay, so 1 over 1 times 1 choose 0 times 1 to the power 4, which is 1. And we have 14 as the answer. Okay. So you can see that for small numbers, maybe it is easier to just list all the cases. Okay? You can always apply this formula. Okay, and the advantage of this formula is that you can even program it to automatize the calculation. Okay? But for small exercises, if you calculate only once, then maybe for small numbers it may be faster to just use or do the calculations by hand. Okay, so so that answer that was an application of the second remark here. Okay, so here in the previous example we have k boxes, but we allow some boxes to be empty, so we need to calculate this sum. So this was the previous example. Okay. So if you have only one non-empty office, then we use the formula for the Stirling numbers of the second kind. Obtain this. If there are 2 non-empty offices, then we have okay. Then we have 7 ways. Or if we have 3 non-empty offices, then we have 6 ways. In total, we have 14 ways. It's the same result that we obtain by listing all the possibilities. Okay, so here is an identity to calculate the Stirling numbers of the second kind. Of course, in order to prove this identity, you can plug in the formula that was given, okay? Or just add many different combinatoric identities. You can use a double counting argument, okay? So here, the left-hand side count the number of ways to put n+1 balls into k non-empty boxes. Okay. But here, how can we design a procedure to count the number of ways to put n+1 balls into k boxes, so that to obtain the the right hand side. So here we fix the box number n+1. Okay. Sorry. Now we don't fix the box number n+1, but the ball number n+1. Okay. So let us consider the ball number n+1. So there are two cases. Okay. So one way to arrange the n+1 balls into k boxes is to first arrange. So there, if we look at the ball number n+1, then excuse me. Okay, so we look at this ball. So there are two cases. Either this ball is in there is one box. It is in its own box. Okay, so it doesn't share its box with any other balls. So if n+1 occupy this ball occupy the whole box, that means that the other n balls should be distributed into k-1 boxes. Okay. So if this ball number n+1 has its own box, then the number of ways to arrange is equal to, there is one way to put this ball into a box, because the boxes are the same, times s and k-1. Okay. And the other case is that this ball share a box with some other balls. So in order to ensure that this ball number n-1 share a box with some other balls, we will first put the other balls into k boxes, so that all the boxes are non-empty. Okay, and then only after that we choose one of these k boxes to put the last ball into it. Okay, so then put the ball n+1 into one of the k boxes. Okay, and you know that in order to put n balls into k boxes, so that the boxes are non-empty, we have s and k. Okay, and then we choose one of the boxes to put the last ball into it. We have k ways to choose a box for the last ball. Okay, so that gives you the two terms of this right hand side. So all in all, we have counted the number of ways to put n+1 balls into k boxes, so that none of the box is empty. So since we count the same objects, we must obtain the same result. So we have this identity. So is it clear for everyone? Hello? So do you understand the idea of the proof? Okay. So you can note that this is n into n balls into k boxes first, and then choose one box for the last ball. Okay. And then this corresponds to the case where the last ball is alone in its box. Okay. Then you distribute the other balls into the other kind k-1 boxes. Okay. Okay, so this proof here is a little complex, but you know the idea. Okay, so the last case, identical balls, identical boxes, is in fact a very difficult case, which up to now we don't have any exact answer. We don't have a beautiful formula for this. In fact, you can, if in the case where the balls are the same and the boxes are the same, you can think of it is the number of ways to put the balls into the boxes. It is in fact equivalent to write such a way is equivalent to a way to write a number n as a sum of integers. Okay, and since the boxes are identical, we should in order to avoid repetition, we should order the boxes in a decreasing number of size. Okay, so one way to write n as the sum of k integer is called a partition of this integer n. Okay? And if you are interested in partitions and the stories of partition, there is a famous Indian mathematician who was considered a prodigy. He gave a formula for the partition, not an exact formula, but an approximation, an approximate formula, which is quite surprisingly. Oh, surprisingly exact, surprisingly good. So the name of that mathematician is, I guess some of you, Ramanujan. Okay, so he was considered a genius, a prodigy. He didn't have a proper education, but he was very good at math. So good that some famous math professor from England brought him from India to Oxford to do math. But unfortunately, since he didn't cope too well with the cold weather in England, he died at a young age. And that I think that there were recently a movie about him, which is if you are interested, it should be The Man Who Knows Infinity or something similar. I'm not sure. I don't remember the name exactly, but you can look up information on him if you want some inspiration. Very beautiful story. Okay, so that with the a brief introduction to the partitions, integer partition, we have finished the slide on generalized permutations and combinations. So I propose we take a short break, and then after the break
Excuse me. So is it a negative where AI is greater than 0 or greater or equal to 0?
No, here the numbers are positive integers. For example,
But why does it have to be positive? Well, and while it's
for example, 4, you can write it as 2 plus 1 plus 1, or 4, or 3 plus 1, or what else? 1 plus 1 plus 1 plus 1. There are many objects in combinatorics which are linked to each other and linked to the partitions.
So I mean that there can be 0 balls in one box. That's what I mean.
No, in fact, when we the question is when we want to count the number of when we want to count the number of ways to partition an integer into as to write an integer, a positive integer, as the sum of different positive integers. We consider all these possibilities. The k here is not fixed. Okay? K can go from 1 to n. Here, k is equal to no, consider only positive integers. Okay? Only positive. So they should be. Okay. So k here is at least 1 and at most n here. Okay? So for small numbers, you can list all the ways to partition an integer, but there is no closed formula. Okay? So Ramanujan gave a formula, an analytic formula, which gives an approximation of the number of partitions of n when n is large. When n is large, then it is quite good. It is asymptotically good, but we don't have any closed form formula. And that is a very difficult subject in combinatorics. So that's why here.
You mean that you mean that there are all the boxes must be non-empty. Is that right?
Yeah. Exactly. But here you are so that means that this is not you don't consider this. This is the same as this way. Okay, so each way is only counted once. Okay, so let us take a break, and after the break, we will talk about recurrence relation. Okay.
Okay.
Okay, so let's start with a new topic on recurrence relation. Okay, so as usual, in order to better illustrate the use of recurrence relations, we will start with some examples. Okay, so here is a classical example involving recurrence relation. So I guess that some of you have already heard of the Fibonacci sequence. So it was an ancient puzzle, which can be stated as follows. So on an isolated island, uh, they put a young pair of rabbits. Okay, so the rabbits reproduce very quickly, but the young newborn rabbits do not. Is it okay? You see the correct slide. Okay, so now suppose that we initially we have a pair of rabbits, and newborn rabbits need 2 months to be able to become adult rabbit that can reproduce. And in this puzzle, we suppose that the rabbits do not die, and that means that after 2 months they will continue reproducing forever. And after 2 months, each pair of adult rabbits can give birth to another pair of rabbits every month. Okay? Now the question is that what is the number of pairs of rabbits on the island after n months? Okay, so in order to solve this puzzle, we need to write down the first numbers of rabbits to have an idea, to have an intuition how the number of rabbits increase. So we will create a table for each month. So since the rabbits need 2 months to develop, we will use 3 columns here. So on the rows are the number of rabbits in each corresponding month. And here the first column is the number of pairs of rabbits of 0 month old. So initially we have one pair of rabbits of 0 month old, okay, and 0 and 0 here. And then we have, after 1 month, we no longer have a pair of young rabbits, but the pair of the initial pair of rabbits now become 1 month old. 1 month, 0 month, 1 month, and this 2 months. And then at the second month, we have one pair of adult rabbits, which will give birth to one pair of newborn rabbits here. Okay, so here we have a total 1, 1, 2. Okay. And then after another month, we have one pair. This pair of newborn rabbit becomes 1 month old. We have no new adult rabbits, and we have another pair of rabbits. There's 3 here. Then here, this pair of rabbits will move to here, and these 2 pairs of rabbits will give birth to 2 new pairs of rabbits. And this pair move here, and we have 5. And after that, we have 3 here, which give birth to 3 here and 2 here. So we have 8. Okay. So what is the pattern here? In fact, here you can see that in fact the number of new pair of rabbits at this month here is equal to the number of pairs of rabbits which are at least 2 months old. Okay. So I will change the color. So this number, you can see this number is equal to this number. Okay. In fact, the difference between 2 rows is the number of rabbits, of newborn rabbits here. So here you have 2 pairs of newborn rabbits, which that's why you go from 3 to 5. Okay. The rabbits which are 1 month old or at least 2 months old are already there, so they are already accounted for in the number of rabbits of the previous month. But the increase comes from the number of newborn rabbits. Okay. So here, what is but here we want to establish a relation between the numbers on this column. We know that here 3 is equal to 2 plus this number. But what is this number? This one here is in fact equal to the sum of rabbits which are at least 2 months old here. And we know that the number of rabbits which are at least 2 months old here must exist 2 months ago. That means that the number of rabbits which are 2 months old here is equal to this, and you can see the relation. Okay. So 8, for example, here, if we so here, for example, 8 is equal to 5 plus this new number, which is 3. And 5 is equal to, you can see 3 plus 2. 3 is equal to 2 plus 1. And you can continue the table, and you can see that this rule we keep on repeating forever. So the observation here is that the total number of rabbits at each month is equal to the sum of numbers of rabbits of the 2 previous months. Okay, so this is the fixed form. So for n from 3 onwards, when we count the number of pairs of rabbits after n months, we divide these rabbits into two categories. So the number of pairs at the previous month, since the rabbits don't die, if at the previous month there are f(n minus 1) pairs of rabbits, then they will carry over to the current month. Okay, and then we need to add to this number to this number of the previous month the number of newborn pairs. Okay, so here it comes here the clever observation here is that the number of newborn pairs, since we know that each pair of rabbits after 2 months produce another pair. That means that the number of newborn pairs at month n is equal to the number of pairs of rabbits which are at least 2 months old at the month n. So the number of pairs which are at least 2 months old at month n is exactly the number of, is equal to the number of rabbits if a pair of rabbits is at least 2 months old at month n. And that means that this pair of rabbits must exist already at month n minus 2. Okay, so that means that the number of pairs which are at least 2 months old at month n is exactly the number of pairs that exist already at month n minus 2. Or in other words, the number of newborn pairs of rabbits at month n is exactly f of n minus 2. And so we have only old rabbits and new rabbits, and we take the sum to obtain this relation. For n for n greater than or equal to 3. Okay, so an equation like this involving the index n is called a recurrence relation. So you can see that here there are two parts. A recurrence relation is defined by an equation, okay, for n. But so if we have a recurrence relation, then in order to calculate fn, we can calculate backwards. We will calculate fn minus 1 and fn minus 2, and in order to calculate fn minus 1, we need fn minus 2 and fn minus 3, and so on. So if we trace back, then at one point we need some initial values in order to start our calculation. So those initial values are called the initial condition. Okay. So if you have a relation like this, it tells you about how the terms of a sequence relate to each other. But in order to calculate the exact value, you need the initial conditions. Okay. So this sequence of fn, which satisfies this recurrence relation with initial conditions here, is called the Fibonacci sequence. It is a very important sequence in combinatorics. You can see that it appears not only in mathematics but in real life. There are many structures or many things in nature which have the Fibonacci sequence underneath. Okay. if you look up Wikipedia for Fibonacci sequence, you can see a lot of images. For example, the arrangement of the sunflower seed in a sunflower will give you some pattern that remind of Fibonacci sequence. Or the or there's some famous the golden ratio in architecture is also related to the Fibonacci sequence, and so on. Okay, so the second example is a famous example for those who do computer science. Okay, so do you know of this problem, this puzzle Tower of Hanoi? The Tower of Hanoi. No one knows exactly why it is called the Tower of Hanoi. But the statement is like that, and you may encounter this game at math open days or some activities for children. Okay, so basically this game can be played with some disc with a hole in the middle so that they can be put to the three wooden plates. Okay, so the setup is this one. Initially, there are some discs put on one plate. There are three plates, and you have to. The goal is to move all the discs to another plate. But you have to follow the rule. That means that at each step, you can only move one disc. And secondly, all along the game, you can never place a disc on a smaller one. That means that if you, so this is allowed, this is allowed, but this is not allowed. Okay, so at any moment in the moving procedure, the disc must be placed so that the bigger disc is below the smaller disc. Okay? So I guess that some of you may have already known this problem or may have even played the puzzle, the wooden puzzle. But here the question is that how many moves does it take to move n discs from one plate to another? So there is a legend that in a monastery far away, there are three golden plates and 64 golden discs. Okay, and the monks in that monastery, their job is to move the 64 discs from one plate to another. And the legend says that the moment that they finish moving the disc will be the end of the war. And so we will try to answer the question that how many moves will it take the monks to finish the war? Okay, so here you can try for example with one disc is trivial. Okay, with one disc, then you need only one move. So what about two discs? The two discs, first you move this one to here, you move the smaller disc here, and then you move this one to here, and then you move this one to here. So it takes us 1, 2, 3 moves. And what about what about 3 disks? Have you tried? Are you trying yourself? If you have 3, you can try it with your books, with your small object. So this one should go here or here. Okay, either one. One. Okay, and then we move this guy here. With 2 moves. And then the only 2 possible moves are either here or here. So we move this here. Okay. And then we move the bigger one here. And what else? We should move the smaller disc here. And then we almost finished. We move it here, and then we move it here. So how many moves are there? So I hope you have followed and counted. But then the number is 7. Okay, so I guess some of you might have already known. So the idea is that we denote, we will establish a recurrence relation to calculate the number of moves. So let's call H1, Hn, the number of optimal, the optimal number of moves in order to move n disks from one peg to another. Okay. So what we will do is that, so in order to move n peg, first we need to remove the top n minus 1 disk, so that the lowermost disk, the biggest one, is free. So in order to, so first we have something like this. Okay. So we have a big chunk here. So this is n minus 1. So in order to move in order to this biggest disk to be able to move, we need to free the disk on top of it. So we will move these guys here. Okay, so this will take us Hn minus 1. Okay, because it is similar to the problem to move n minus 1 disks from one page to another. Okay, so Hn minus 1, and then we move the big one here, which will cost us 1 move. And then finally we move the big pi here, which will cost us another Hn minus 1 moves. Okay, so all in all, we will have to use Hn minus 1 plus 1 plus Hn minus 1, which is equal to 2 times Hn minus 1 plus 1. And does anyone know the formula, a closed form formula for Hn? Does anyone know?
I think it's the 2h n minus 1 plus 1.
Hmm, so you can guess. You can guess. For n equal to 1, you have 1. N equal to 2, you have 3. N equal to 3, you have 7. What will be the next one? Equal to 4. That's 2 times 7 plus 1, that much. Yeah. So you can guess the closed form formula is 2 to the n minus 1. So which is a function that grows very, very fast, exponentially. So you can so if we consider our relation of the monks that move the disc at the faraway monastery, then they will need 2 to the power 2 to the 64 minus 1 moves. Okay. So for those of you who are quick with calculation, you can assume that they need 1 second for they need 1 second to move one disc. So that means that they will need this many seconds. And you can plug it into your computer to see that it will be long after the sun has died. Okay, so we don't have to worry about the monks who moves the disc at a faraway monastery, because we will not live to see that day. Okay. Okay. So this is the approximate answer. You can see that it has how many zeros. It is larger than the sun will die in 10 billion years. Okay, 10 billion years. That is how many. So here you can divide it by 365 times 24 times 3,600 to see how many years will this be. Okay. Okay. So that we will continue with another example of use of recurrence relation to solve counting problems. Okay. So up to now, you have seen that we use recurrence relation when we need to count the number of objects in sets which are whose size are characterized by n. So here, for example, in the first in the first example, if we call Sn the set of rabbits, sorry, not rabbits, but the pairs of rabbits, at month n, then what we are interested in is the size of Sn, okay, which will be denoted by Fn. So we will, in fact, here our counting problem is to count the number of elements in a set which have n as a parameter. Okay. So in this example, our set is the set of optimal moves for n disks. and we want to determine the size of that set. And here, similarly, in the third example, we consider a system of code word. So each code word is a string of digits. That means a string of characters from 0 to 9, such that the number of zeros in it is even. So, for example, 0, 0 is a valid code word. 0, 0, 1 is valid because there are 2 zeros, but 1, 0, 1, 0, 1, 0 is not valid because there are 3 zeros, or 3, 4, 5, 1, 8 is a valid code word because there are 0 zeros, okay? But 9, 0, 1, 2, 3 is not valid because the number of 0 here is up. Okay. So here, for example, here you have 2 zeros, and here you have 3 zeros. So the first word is valid, and the second word is not valid. And now, what is it that we want to count? So we will divide the valid code word into sets according to the length of the code word. So let us call Sn the set of valid code word of length n. Code word of length n. Okay. Then we want to determine the size of these sets. That is, we want to define an, which is the size of this set of valid code words of length n. Okay, so let us for some smaller n equal to 0, we have the empty word. So we have one valid code word. Okay, so n equal to 0. We have one valid code word, which is the empty word. So we have a0 is equal to 1. Or if you sometimes you want to count from n equal 0, and sometimes you want to count n equal 1. So it depends on your setting, depends on what you want to do, depends on what you want to count, depends on your particular problem that you may want your sequence to start with the index 0 or with the index 1. Okay. So if n is equal to 1, you have exactly 10 code words. 10 words. But this one is not valid, and all the other ones are valid. So yes, a1 is equal to 9. Okay. And for a2 it's a little more complicated, because if you list all the words, then for n is equal to 2, there are in total 100 words. So it is not very practical to list all of them. So now we will try to find a recurrence relation between the terms an and our sequence in order to find a formula for an. Okay, so what will we do? So we observe that. So a natural idea is to create a code word, a valid code word of length n from a shorter word, from a word of length n minus 1. Okay. So if we consider a code a valid code word of length n. So let's call this valid code word b1 to the n, where bi's are the digits. Okay, so we distinguish two cases. Okay, so if the n is not 0, if the n is not 0, then this word w is a valid code word if and only if the word w prime, which is obtained from w by deleting the last digit, is also a valid code word. Valid. Okay. Of course, the other case is the n, the last digit, is 0. If the n is 0, then the word w prime, does it have an even number or an odd number of zeros? Since w is valid, if the w is valid and we delete 1 0, then what remains will not be valid. Okay, because once we remove 1 0, we change the parity, we change the oddness and evenness of the number of zeros in the word. Okay, so we have two cases, and now we will try to count the number of possibilities in each case. Okay, so in the first case, since dn is not 0, we have 9 choice for dn. Okay, and we need to choose a valid code word of length n minus 1. So we have a n minus 1. And we use the sum rule here. Here we have only one choice, which is dn equal to 0. But how can we count the number of invalid code words? We know that of all the words of length n minus 1, there are only two types. They are either valid or non-valid. So we will take the total number of words of length n minus 1, which is 10 to the power n minus 1. Okay? Because at each position we have 10 choices. And since we are counting the number of non-valid words, we must subtract the number of valid words from it. Okay? So here is a recurrence relation for the number of valid code words of length n. Or if you want to simplify, you will have 8 times an is equal to 8 times an minus 1 plus 10 to the power n minus 1. So let us check with some small values of n. So you know that n equal to 0, we have 1, okay. N equal to 1, we have 9. So the formula verifies, okay. So you have 8 times 1 plus 10 to the power 0, which is 9. So you can continue. You will see that the number of valid code words of length 2 will be, I don't know, can someone help me? 72 plus 10 should be this, right? And so on. So this sequence also seems to increase exponentially, and we will see later when we talk about the formula to solve recurrence relation that indeed these types of recurrence relation, we have a solution. The general term will increase exponentially in n. Okay, so everyone understands the example is 8 times 9 plus 10 to the power 2 minus 1. Okay, so it is 82. And you can continue on to see what is the value for n equals 3. Okay. So here is a written form of the solution. But the idea that you have to keep is to consider two kinds of coordinates in function of the last digit. Each di is a digit, is a letter or character. The whole thing is a string or word. In our context, string or word are synonyms. Okay, string or word. In our context, they are the same thing. They are just a sequence of characters. And here in this particular case, the characters are the digits. So we have a string of digits. Okay. And we call each string sometimes or quite commonly in computer science or in mathematics, we can also call those things words. So in mathematics and computer science, when if you see people talk about words, then sometimes you should understand that they mean string. These words may not have meaning. Okay, they are just a string of characters. So here you know that we distinguish two cases, and then we obtain this. Okay, so I guess we will stop here today with these examples, so that to let you have time to catch up in the tutor class. And next week we will talk about more technical things. We will see how to solve recurrence relation. Okay. So are there any questions? Hello?
No.
Okay, so if there are no questions, then goodbye and see you next week.
Goodbye, teacher.
Bye, teacher.
Bye, teacher.
Goodbye, teacher.
Bye, teacher.